Hello, my name is Max Mahalik, and it is the 5th of May. And I decided to do my portfolio project on the anatomy and enzymology of fat absorption. So, first of all, to just kind of give a basic overview of fat or lipid digestion, I just kind of wanted to run through that real quick. So in the oral cavity, this is where digestion is going to start. There are some lingual lipases in there that will start to break down triglycerides, and then also the mastification or chewing, that mechanical breakdown of fats. Then moving on to the stomach, we have gastric lipases. Down here we also have lingual lipases being somewhat active, not as active as they are in the mouth. Breaking down triglycerides, and then we have some mechanical breakdown, forming these crude emulsifications, breaking up the aggregates of lipids using the peristaltic waves of the stomach. And then moving on to the small intestine, this is where most absorption and digestion of fats occurs. Very importantly, we have pancreatic enzymes being released in the small intestine, and then we also have bile being released into the small intestine. And within the bile, we have the bile salts, which further aid to emulsify the fats and break them up, increase the surface area, so enzymes can get in there. There can be more enzyme to substrate interactions, and therefore we can have a higher degree of digestion. Additionally, here the bile salts helped form these micelles, which I'll talk more about bile salts and micelle formation and how that all works on the next slide. But as I said, there's pancreatic enzymes. The pancreas is releasing lipases. It's releasing colipase. It's releasing cholesterol esterase, phospholipase, a lot of essential enzymes for the breakdown of fat that I'll get into here. So first, I just kind of like to give a rundown of bile salt emulsification. So within the bile, we have, first, the bile is made in the liver. It's made by the hepatocytes, and it's secreted from the gallbladder. The gallbladder is where it's stored. And within bile, it contains these bile salts, contains bile pigments like bilirubin, and then it also contains cholesterol. And then sometimes it contains some harmful substances that the liver has filtered out and that it's excreting to the small intestine so they can eventually be excreted as feces. But the bile salts are the important component here when it comes to fat digestion. So these are amphipathic molecules. So the bile salts have a hydrophobic and hydrophilic ends, and you kind of see this over here, how they function with the nonpolar and the polar charged ends. And therefore, the polar side is going to want to be on the water surface, and the nonpolar side is going to interact with the fats. And this will allow for these large aggregates of fatty molecules to be broken down into smaller molecules, increasing the surface area and increasing the enzyme to substrate interactions, allowing for further digestion to take place. Although one important factor needs to take place in regard to all of this is we need colipase, which is a coenzyme to many lipases, to be present because it disrupts the interactions between the bile salts and allows the enzymes to get in to these emulsifications and allows the breakdown of fats. Once we have all these subunits broken down and the bile salts kind of still holding things together, these smaller molecules hold together, we have the formation of these micelles. And these micelles are then migrate towards the brush layer of the enterocyte, that unstirred aqueous brush layer, and that's where absorption is going to start. So from there, we have three main fats that are consumed and absorbed by the small intestine. We have triglycerides, we have phospholipids, and we have cholesterol. And so I'm going to run through all of those, starting with triglycerides, as they are pretty much the number one fat that we use as humans, that we consume and absorb. And as I've touched on in the past few slides, there are lingual lipases, gastric lipases, and pancreatic lipases that all play a role in triglyceride breakdown. In triglycerides, all these lipases break the triglycerides down into monoglycerides and fatty acids. And then the monoglycerides can even be broken down further into glycerol and fatty acids. But then how do these subunits of the triglycerides get into the enterocyte? So first, from the apical side, this is where they're going to enter first, from that brush layer. we have small fatty acids. These are less than 10 carbons in length, and then glycerol. These are going to passively diffuse into the cell, so we don't need active transfer of these. But the larger molecules, larger fatty acids, monoglycerides, these are going to need to be transported actively, and we use fat CD36 and fatty acid transport proteins are just a couple of proteins that we know of that transport these molecules, or fatty acids, are key in fatty acid transport into the enterocyte. Inside the cell, these subunits are then going to be transported to the endoplasmic reticulum, and it seems kind of counterintuitive, but now that we've got them in, we're going to actually make them back into triglycerides or higher ordered lipids. And as I say, they're going to be reformed, and then I'm going to touch on chylomicrons in the coming slides and the further aspects of fat absorption. But alongside esterified cholesterol, non-esterified cholesterol, phospholipids, proteins, triglycerides are all going to come together and form lipoprotein known as chylomicrons that are essential for fat transport or fat absorption. So moving on to the next slide, I'll move my face down here real quick so we can kind of get a picture so you can look at these. But cholesterol and phospholipids, these are our next two classes of lipids. So cholesterol, it cannot be absorbed from the small intestine as a esterified cholesterol. So we have the pancreas releases cholesterol esterase, which will break off that ester linkage, break off whatever is connected there, as we can see up the top, to allow for cholesterol absorption. And then through the apical transport, how we get across that apical membrane. It's usually, this has kind of been debated whether it's passive or active transport, but newer studies have shown that it's more active due to the high efficiency of cholesterol that the small intestine can absorb. We think it's predominantly active. I list two different transporters here, NPC1, L1, and ATP binding cassette proteins, both actively transport cholesterol into the enterocyte. And then prior to chylomicron formation, cholesterol can be reesterified. Then that can be transported within the micelle itself, or it can be left as unesterified, and it can kind of be used, the chylomicron, that lipoprotein, the outside's made of phospholipids and proteins, but also cholesterol can be added in there, non-esterified cholesterol. And then phospholipids are predominantly broken up by pancreatic phospholipase A2, and you can kind of see the function down here to our bottom right. And phospholipids are broken down into lysophospholipids and then fatty acids. And then move my face back up. Okay, and to the right here, we're going to just kind of go over chylomicrons now. So now we've kind of talked about how the three main classes are digested in the small intestine and how they make it into the enterocyte, and then kind of a brief summary of what happens when we are in the enterocyte. And now we're going to talk about how we're going from the inside of the cell and the modifications, or in triglyceride, we remade from our triglyceride subunits, we remade triglycerides from our cholesterol, we re-esterified it. And this is all in hopes to make this lipoprotein here we see to our right, known as a chylomicron. And we make chylomicrons are being used because most fatty acids, most lipids are too large to enter through the basement lamina of the capillary, so they can't be taken up through the circulatory system, so we must do this a different way. So this lipoprotein is kind of used in a bulk fashion to transport lipids through the lymphatic system, which is truly fascinating. So kind of talk about the formation. The chylomicron formation starts in the ER with the formation and aggregation of long-chain fatty acids, non-esterified cholesterol, esterified cholesterol, triglycerides, phospholipids, fat-soluble vitamins, and then also apolipoproteins. And this forms this pre-complex, this pre-chylomicron complex that is then transported to the cis-Golgi apparatus. From here, some further modifications and packaging are made. So the apolipoproteins are glycosylated. Further modifications occur, and then a vesicle, or the chylomicron is buds out of the trans-Golgi apparatus in a vesicle that can then fuse with the plasma membrane on the basolateral side of the enterocyte. and then your chylomicron can make it into the interstitial fluid, and from there it can be taken up through the lymphatic system. From the lymphatic system, can go up to the subclavian veins, and through the thoracic ducts can enter into circulation. So it's just another route, or it's the main route of lipid absorption, but it's how we bypass the fact that large lipids cannot make it into the capillaries in the small intestine, or surrounding the enterocytes. But it is important to know that some small fatty acid chains, some small fatty acid chains, and like glycerol, can transport directly into the bloodstream, into the circulatory system. And then on this last slide, I kind of include just an overview of things. I thought this was a really good image, and I normally don't include images as my final slide, but I just thought this is a really good summary. It shows cholesterol, lysophospholipids, long-chain fatty acids, monoglycerides, how they all enter into the cell. We see the endoplasmic reticulum making chylomicrons. We see the modifications. We see the exocytosis of the chylomicron, and then the entry into the lymphatic system. And then additionally, we see the glycerol and short fatty acid chains and medium fatty acid chains, those that are less than 10 carbon units in length, carbon atoms in length, making it directly into the bloodstream. And from here, I also have my resources. Thank you. That'll be all.